My name is Ashwin Ram. I'm a Technical Director of AI in the CTO office at Google Cloud. And we've put this day together for you with one of our leading machine learning practitioners and scientists, Cassie. Cassie has a really interesting background. She has 4 degrees. She has degrees in psychology, economics, mathematical statistics, and cognitive neuroscience. And what she does is look at data using the lenses of statistics and machine learning to bring it together to help people and companies make decisions. Her role is a chief decision scientist at Google Cloud. It just changed from chief data scientist with the office of CTO. So my pleasure to introduce Cassie, and she'll take it from here.
Thanks so much for that introduction. So hello and welcome. My name is Cassie Kozyrkov. I serve as the Chief Decision Scientist for Google Cloud. And it is my pleasure to welcome you today to the wonderful world of machine learning. Now, this course is one of Google's most popular courses, and it is accessible to all of our job roles. So it is specifically designed to be entirely beginner-friendly. So even if you don't know what a computer is, hopefully you should still be fine in this course. Never seen an equation before? Fine as well. So we aim for the big ideas, the flavors of things, because I believe that technical nitty-gritty, those equations and those code things, I really like to do those things, but I don't like it when those things are done to me. So in a class setting, it's excruciatingly boring, at least I think so, to watch somebody copy out a textbook on the board when you know you can go do that yourself with a cup of coffee. That's much more fun. So I'm aiming to give you all the other stuff so that those textbooks, equations, and code snippets make more sense when you are playing with them yourself later. And the focus here is on application, on process, and on big ideas. So let's dive in, shall we? And see what it looks like when a learning system is learning. So this is an AI system learning to play an Atari slider game, Breakout. And when it begins, it is playing, if you will believe it, worse even than I play. I give it a little while longer, and it's a flawless expert. It's getting some pretty steep angles there. And then, see what we want it to do. We give it controls of a joystick, essentially, and its sensory input is this environment. We don't tell it anything about the rules of the game. Tell it just to figure it out, but figure what out? Figure out how to get the most score velocity. In other words, how to get that score to go up as quickly as possible. And so after it trains some more, this little bundle of math and joy is going to figure out strategy. If you wanted to get that score to go up as quickly as possible, what would you do? How do you play? It tunnels up the left side, and look at that score go up. How many of you do this? Yeah, seriously? Okay, wow. All right, I'm impressed. We've got an expert audience in the room. When I gave this presentation in the Tokyo office, it was like almost all the hands. What am I dealing with here? Anyway, now this looks all exciting, it looks magical, and there's all these marvelous buzzwords in this space. Neural networks, AI, machine learning. You're all excited. So, let me take you down a notch. What is machine learning? It's used often these days as synonymous with magical magic. It's a magic box of magic, and we open it up, we sprinkle magic on the top of our business, and magic happens. Actually, let's just put it bluntly. It's something far less glamorous. Machine learning is a thing labeler, essentially. It's an approach to making lots of small decisions with data. Decisions like, is this email spam, yes or no? Or what should I bid on the next auction? How do I move a joystick? And if you want a computer to make decisions for you, it's got to convert information, input data, into an answer, a label, or a decision via some kind of recipe. And the difference between traditional programming and machine learning simply boils down to where that recipe comes from. So where does it come from in traditional programming? Of course, the human programmer must communicate in some way with the universe, think deeply about the problem, channel divine inspiration, and handcraft that recipe as code that the computer will then use to convert data into outputs. Now, in machine learning, we don't handcraft anything anymore. Now the programmer's task changes to feeding examples into the system, and it is the machine learning algorithm's job to stitch that recipe together out of the examples. So that's the difference. Now, why would you use machine learning? Well, let's take a look at a little example. Here I have a completely made up treatment schedule for a patient. From day 1 through day 60, this is the correct dosage in milligrams. And now the exercise is to see whether you are actually alive and able to make noise. So, it is day 2. How many milligrams do we give the patient? 17. Day 4. 41. Day 2 again. 17. Would you use machine learning to solve this problem? Well, how would you solve this problem? I hope you would do a lookup. Just look the answer right up. Don't do any kind of magical learning. There's the answer, why not just look it up? So you don't need machine learning in this situation. Okay, different question for you. It is day 61. What is the answer now? Aha. Well, if there are no patterns here in these data, then you can't actually solve that. Nothing can help you for day 61. Or if there are patterns, but they just simply don't apply past day 60, they don't generalize beyond that, because maybe the patient is now healthy or, I don't know, dead, then, right, doesn't work either. So the only way that you might be able to make an attempt at day 61 is if there are patterns here that you can find and make a recipe out of, and that are still relevant and useful in this new data situation. In that case, you would want to use machine learning. So I'm going to say over and over today that in machine learning, we have one job: succeed on new stuff. That is the entire focus. Do well in new data situations, because how do you deal with the old ones? Just look it up. All right, so how does this magic thing work? We have some data to learn from, and our task is going to be to predict whether or not I like a bottle of wine. So what we have here is the correct classification for 50 bottles of wine, a red Y for yummy and a blue no for not so yummy. And I have the age of the wine in years and the opinion of some amateur wine critic friend of mine on the y-axis here. And the game here is to find and exploit patterns in data. So look at these data and tell me when you see a pattern that you can exploit. Something to separate the yeses from the nos. That's the game. So can you do it? You come up with a recipe that separates them? Nod when you see it. Nod when you see it. All right, I see some people who are finding it. Very nice. And now I have to own up that it's all a trick. Actually, these data, I made them up, and I made them up completely at random. So I know that there are no patterns here. And if you're finding patterns that are sort of spirally or circular, and you think you've got some story that you can base a recipe on, that's your beautiful human mind finding Elvis's face in a piece of toast. Our brains do that. We find patterns that aren't actually there, and then we think that we've got a strategy that we can exploit, and things go wrong when we try to use it. Now, machine learning can do exactly the same thing. Find patterns that are not there. And then if we base our solutions off of those patterns that aren't there, of course things crash and burn. So the approach that we take to protect ourselves, and we'll talk about this a lot today, it's the same approach that we should actually get in the habit of taking with our own human intuitions. Don't take it seriously in the piece of toast where you found Elvis's face. Try it on a new piece of toast and see if the face is still there. So try it in the new data, see if that recipe still works. Whether it comes from a machine or from a human, that's the part that keeps you safe. Okay, enough messing about. I generated these data and I promise you that there is a pattern in here. How would you exploit this pattern to help me classify new bottles of wine? How about you put a line through it, and that line is a wall that separates the red region from the blue region, and off we go. Sounds good? That's pretty much what machine learning does. Now, that boundary does not actually need to be a line. Those gobbledygook algorithm names, which we'll meet later, the main difference between them is the allowable shape of the boundary that the thing is trying to shove through your data. So if you pick this one, it's going to try to put one single line, and that line can have any slope. With this one, now it can use many lines, but the only slope options are thus and thus, vertical and horizontal. Or you can have a real nice flexible squiggly thinger, which we call neural network. And once you have picked the algorithm and the allowable boundary that's represented by it, then what it's going to do is, based on where your data lie, it's going to try to find the most sensible place to put that allowable boundary. So it's going to try to contort itself to your data, subject to the sort of thing it's allowed to be. So say we pick the line, and we run it. Oh, there we go. There's our answer. And what comes out of this is what we've wanted all along, a model. Now, a model is just a fancy word for recipe here. Just a set of instructions to take inputs, turn them into outputs. And our model reads, if we're in the red region, call it red. If we're in the blue region, call it blue. Job done. And so in comes a new bottle of wine. Red or blue? Red. But we could have chosen a different algorithm. There we go. Let's pick the tree and run that thing. Here is our recipe. And that's a different recipe from the previous one, right? And in comes a new bottle of wine. Blue. Troubling. Most troubling. If you look in any textbook and ask, what is a reasonable, classic, respectable algorithm to use for this situation? Some textbooks will tell you this one, some textbooks will tell you that one, some textbooks will tell you both with a completely straight face. These are the things you need for this situation. Okay, so then you follow the textbook's advice and you end up in this situation where one of them says we'll like the bottle, one of them says we'll hate the bottle. They can't both be right. So which one of them is lying to us? Who is the imposter? How do we tell? Well, we remember that the whole point is, does it work on new stuff? And so we simply see which one actually does work on the new stuff. The point is to generalize beyond our data. So that is how we evaluate. Let's find out who wins on new data. So in comes some new data, and we apply both of our recipes to it. And of course, we get different answers. And I'd like to remind you, when we ran these two algorithms on our initial dataset, the training dataset, they both gave perfect performance. They managed to split the space so all the red went to red and all the blue went to blue. No mistakes. So both of them had 100% performance scores. But now, look at these results. Because they're different, one of them will probably be worse than the other. So let's find out who. How? Well, let's drink some wine for science. Here are the correct answers for that dataset. And all we need to do for our fancy statistical testing, never mind what models it all came from, you can forget all that at this point. Compare the desired answers with the answers given, and I feel like I have a preference here. I don't know if anyone else does, but I sort of strongly prefer the one on the left. And then I would iterate towards my solution with that one. And I would do a careful launch test before launching it, which we'll talk about later. So what is machine learning? It's an approach to making repeated decisions that involves algorithmically finding patterns in data and using these to make recipes that deal correctly with brand new data. Okay, now what's under the hood? How does it decide where to put that thing? What's inside that black box? Surprise, it's full of math. And on our menu today, we are going to meet the flavor, rather than the equations, of a whole bunch of algorithms. But here's how we're going to do it. Right now, I'm going to introduce you to this one. And my goal is to set your thinking about these algorithms. What are the important ideas here? And then later, when 90% of you have fled and gone home or went to play outside, at the very end of the course, after we've covered the end-to-end applied machine learning stuff, we're going to look at all of those. So let's dive in. Regression was first used in 1805 by Legendre, who doesn't have a nice painting of him on Wikipedia, so I picked the one for the second person to use it in 1807, Gauss. So that's more than 200 years ago. This has been around for a really long time, and it's still a really popular standard approach to machine learning today. So let's have a look. For our example, we will be making smoothies. Every smoothie will have 1 cup of plain yogurt, 1 secret ingredient, and a bunch of random food dye so that you cannot tell what is in there. I blend it up, I serve it to you, and your goal now is to shout at me, what are the calories in this smoothie? Go. What do I hear? 100. 100. Going once, going twice. 300. 500. Now, I'm doing a little test here, seeing who's got the strongest aptitude in the audience for machine learning. Because the machine learning attitude is not the attitude of perfectionism, of think carefully and get the answer right on the first go and don't even try it unless it's going to be perfect. No, the attitude is go for it, see what happens, get it wrong, because you're going to have to do it over and over again. You're going to fail, fall down over and over again, pick yourself up, try again until finally it works. And you have to try something to know what to do next. And so if you're too afraid to start, you tend not to do well in applied machine learning. So those of you who are brave enough to just go for it even though you didn't know the right answer, yeah, that was what's going to get me to move to the next slide and give you more information, and we'll be able to iterate towards correct together. Okay, so you've unlocked the next slide. Turns out this was, what was the secret ingredient? 58 delicious grams of sardines with 265 calories in there. Lovely. I see you don't want to drink it. Fine, I make you a different one. Guess the calories now. 80, 400. 180. All right, I'm hearing some more responses and rumblings. Now let me tell you what was in here. 50 grams of not delicious waffles that I've shown you in the picture. No, the raw stuff, waffle mix. And this is actually an homage to a standard hazing experience that happens on the 5th floor of the Google office here in New York, which is most new Googlers, myself included, I've done this. You walk up and you see this delicious smoothie and you try it and it is not a smoothie. So standard newbie hazing experience here. Okay, so you don't want to drink this one, fine, I make you a third one, but before I make you guess, I'm going to give you a little more information. This is the 16th smoothie that I've made, and here are the 15 previous calorie amounts. Your first reaction to this should be not trying to read it, but instead stamping your foot and saying, I'm a human. I don't add numbers up. That's what machines are for. Indeed, correct. So the machine's going to help us out and summarize them. And we find out that the average is 237 and the middle thing is 240. Have a guess now as to the calories of this one. 237 I'm hearing, 238, 240. Notice how your range has narrowed a whole lot as I give you more information. That's going to be key to our discussion. Okay, I'll go for 237. It turns out to be 88 grams of quiche Lorraine, clocking in at a whopping 445 calories and proving to us that any liquid diet is beatable. So how did we do? We had an underestimate of 208 calories with that strategy. And can we do better? Well, maybe it would help to have the weight of the secret ingredient. So what we'll do as analysts is we'll make a little plot, and we'll have the weight from 0 to 200 grams on the x-axis and calories from 0 to 500 on the y-axis. And as we look at this, we ask ourselves, is there anything going on, or is weight completely useless here? What do you say, completely useless? Something to it. And since there's something to it, maybe we'll go ahead and we'll try it out, shall we? And regression is about putting lines through stuff, so why don't we put a line through it? You like that line? Good line? We missed. Where should we put this line? By the way, those who forgot how lines work, here's a handy cheat sheet. The recipe, the model, is simply intercept plus slope times the weight. So we'll have two numbers here in red that we have to find or discover that determine where the line goes, and then we pop the weight in there and read the calories off of it. So that's what we're dealing with, straightforward stuff. So you don't like my line? Okay, fair enough. How about that one? You don't like that one? This one? It's a tough crowd. That one? No. This one? You look offended. Why do you look offended by this? Because let me remind you of something real quick. This right here, this is your previous model. And now you're offended. But before, you were very happy to just guess 237 every time. 237 and 0 times the weight means I ignore the weight and say 237 every time. And you were so fine to use it then. Check your feature engineering privilege. What is feature engineering? That's when we create inputs that we might use to learn from. Stuff that might inform our solution. And when we have a feature that we might use, suddenly we can do better. So that's kind of going to be the point here. As we get information that's going to be relevant to solving this thing, we expect to do better and better, and it's going to be up to us to think about what information might be worth putting into the system in the first place. Okay, so let's do better. If we can do better, we're going to find a line that's as close to the points as possible, because you seemed offended when I wasn't doing that. Fine. So we better define a notion of an error. What's an error? It's just the point minus the line, the truth minus what we were saying we should predict. And because we all have type A personalities here, we hate errors. So we are going to minimize a function of these errors. That is going to be the score for how this thing performs. And a good score is to have fewer errors, and we will use the RMSE here. And this thing is very creatively named. It's actually the recipe for calculating it backwards. Get the error, square the error, take the mean or average, and take the square root of that. Root mean squared error, or RMSE. Okay. Or you could just think of the RMSE as the calories we're off by on average. Not technically correct, but good enough for government work. We're off by about 85 calories on average, and that'll do. That'll fine for a morning. So now we're off by 85, and we want to be off by fewer. So let's see if we can just jiggle those two parameters there in the recipe to make things better. What do you want to do? Maybe you want to increase the slope a bit. Okay, that's getting better. Good. How about we increase the slope a little more? Not so much better. Maybe now we want to move the intercept down, so let's do that. And what we could do is we could continue tinkering with these two numbers, with slow, boring tinkering, or we could get on with it. So what are our options? Just play by hand with those two numbers, which is what we were doing, Or we could use calculus, but who even does calculus anymore, so old school. Or we could just use an optimization algorithm to get us the answer immediately. So what does an optimization algorithm do? It says, for this setting, you are trying, what's your goal? You are trying to get this function right here to be as low as possible. Let me figure out for you what settings on those two parameters that I'm allowed to play with give me the best possible performance here. And then it outputs you that answer. And that's going to be in the heart of every machine learning algorithm. So we're going to need to know what the scoring is, what the goal is, and then it's going to figure out where to set the free parameters in the recipe based on that. Okay, great. And we have come a long way. I'm impressed with us. Nice. Let's look at quiche Lorraine, though. It's taunting us. We did not predict quiche Lorraine well. How did we do? Better. Our underestimate has gone down. Okay. Can we do even better? Can we? Well, there ain't no such thing as a free lunch, she says at Google. To do better, we actually need something else. So what is it going to take? We need, any guesses? More information, exactly. That was actually very nicely put, because that says two things at once. More information in the sense of just more of the same data, or more information in the sense of other kinds of information that might be helpful. In other words, more features. Features in this setting refers to variables, attributes in other settings. So I'm going to be generous, and I'm going to give you the fat percentage. How do you feel about that? Is that going to be helpful? All right, so let's see. So this is what we were working with before. This is our form, and we just had to muck about with these two parameters here. And we used an optimization algorithm to set them. And notice, who here has taken a stats course of some kind? Yeah, you probably saw regression. It was an entirely different story in that course, the way that you were going about it. There was all this other stuff about what it means, and p-values and t-tests. None of that is relevant here. All we are trying to do is optimize that function to set these two numbers so that the difference between the calories predicted and the actual calories is as good as possible. That's it. That's all there is to it here. Much, much simpler than what the stats course did. So there we go. Those are our answers. Lovely. Now, it's not going to be a line anymore if we add fat percentage. It's a bird, it's a plane. Same structure, just we had another one of these right here. And now the only pertinent thing for you to realize is that there are 3 widgets to tinker with. Nice. And plotting it there, we need to add a dimension. I can't make heads or tails of this, so a little shout out to better plotting. How about adding color? Okay, still not enough, because I can't see what's going on. The color is more calories, gets redder, but I can't see what's going on with this fat percentage and weight plane, so okay, now I can kind of see what's going on. And if you're used to looking at these things, you kind of see the punchline that's coming. But even if you don't see it, let's find out what happens if we run the algorithm. So again, our job is to get those 3 numbers to be as good as possible. We have our 3 options. I pick the getting on with it. And so we have this mosquito netting fitted through our data for us. What is it trying to do? Get as close to our points as possible. And those are the numbers that do it. Quiche Lorraine is still taunting us. How did we do? We are now off by 47 calories on average. Before, it was 49. I don't know, I'm not feeling it. I had to double the number of ingredients into my recipe, and all I get for that is this measly tiny improvement. Maybe after all, this isn't such a promising direction to go in. Maybe I would prefer the simpler model, but of course, don't worry about that too much. You can always try both of them in a new dataset and see which one is working better. So how are we doing so far? Using only the mean. There's our underestimate. With simple linear regression, that means 1 ingredient. We've improved. And only a slight improvement with multiple linear regression. That means more than 1 input into the model. All right, I'll take a question.
Can you do a model that has fat percentage times weight? That's actually tells you how much fat content it is.
Can you do a model that does fat percentage times weight? Absolutely. And there's a good reason to think about doing that, like the bit about the water amount of the secret ingredient. We didn't even cover that, right? If I just dilute the secret ingredient, I can mess about with the fat percentage. The reasoning around whether or not you should go ahead and try a model like that is, does it take a long time to try it? If no, just do it. Even if you don't have as solid of a logical argument, try it anyway. You can always try something like that, and yes, it's very, very easy to adjust the method to input something like that. You just make the feature by multiplying them first, and in it goes, job done. So certainly could try that. Okay, can we do even better than that? Sure, how about if I'm really generous? This is non-alcoholic, and I'm going to give you the fat in grams, the carbohydrate in grams, and the protein in grams of our secret ingredient. Does anyone want to spoil the punchline for us? Who knows about nutrition? Let's have it.
9 times fat plus 4 times carbohydrates plus 4 times
9, 4, and 4, the magic numbers. Because we as humanity have figured out a whole lot about nutrition, and we already know the answer. Well, doesn't matter if we know the answer, why don't we see if we can recover that same answer from this data set with machine learning? But yeah, let's hope that our final answer is going to look something like that answer. So here we go. This thing is now not a plane anymore. It's now a hyperplane, so let's go ahead and plot it. Let's not. There's no real reason to be plotting it here, because at the end of the day, the way that we check how well we're doing, how we get that score that we're optimizing, it happens the same way no matter what is in here. All we need to know about is that we take what's predicted, we compare it with the truth, and we see how we did. And inside this thing, however beastly it is, there are some numbers that we are allowed to tinker with, and we'll use an optimization algorithm to do the tinkering for us, and hopefully some researcher somewhere has written that optimization code so we don't have to. Because that's a much better thing to spend your time on if you're in a research division, or a research in industry, or a research division in academia. Good, and they have, and so we don't have to worry about it. All we need to know is 4 things to tinker with. We'll still assess the results the same way, doesn't matter what's there. So let's get on with it and use that optimization algorithm, which we don't need to know how it works. And there you go. How did we do? 9, 4, 4, something like that. Looks pretty good to me. FDA, by the way, confirms what you say. This is a quote from their website. Carbohydrate provides 4 calories per gram, protein 4, and fat 9. So very good general knowledge. What on earth is this 143 thing? Well, we ask ourselves, if there is no fat, no carbs, and no protein, if our secret ingredient was water, what's left? Well, there was yogurt in there every time. Now, it turns out our yogurt base had 145 calories. We're predicting 143. There's a little bit of a mismatch, so maybe there was some error in our data. But you know what? Our score is getting pretty good. Not perfect, but pretty good. We're off by 4 calories on average when it used to be 47. And this is, again, a shout out to feature engineering. The fact that you had the knowledge about this domain and realized that having the weights in grams of all of these things was going to be useful, that is the reason that you get a model that's this good in the end. It pays off. You can convert your domain knowledge into good solutions. And how did we do in the end? Our underestimate for quiche Lorraine is only 4 calories. I say good enough, let's drink it. Okay, and we will see the other method flavors for that big laundry list at the very end, and you can stay for that if you're interested, or flee earlier if you're not. Right, so what is AI? Well, it depends on whom you ask. AI was named a pretty long time ago, in the 50s, artificial intelligence, and back then it kind of meant something else in regular usage. And I wonder sometimes whether today's calculators would have seemed like AI to folks in the 50s. And sometimes I like to joke that that version of AI was whatever would have impressed those folks, and whenever that was achieved, you just move the goalposts away a little bit. But in that old school sense, it is a sort of superset. And machine learning would be in there somewhere. Where machine learning is, let's remind ourselves, thing labeling, using examples. But the way that AI is talked about today is actually something else. It's more of a subset to machine learning. So let's have a look at some AI tasks and see what they have in common. There are tasks like figuring out whether an image has a cat in it or not, having a natural sounding, human sounding conversation, playing games that you don't know the rules for, that you have to use intuition to figure out the rules. Well, when you, the human, do these tasks, you are taking in information through your senses, and you get the answer as if by magic. You don't even know how you know that's a cat. You don't know how you know how to move that joystick in that game. You just know it. You do something with these pixels, and you don't know what you do. Now, think about trying to solve a task like this the traditional way. You have to really think hard, brainstorm what to do with every pixel, and then give the computer those instructions by hand. Here's how you take the pixels for this photograph, and here's how you figure out whether it has a cat in it or not. Now, what recipe are you going to write? And as you're thinking up that recipe, are you sure it's still going to work for that situation? It's pretty hard to write these rules. You need complicated instructions to do this task. And you have the benefit of eons of evolution. Your brain just does this. You have no idea how it does it. And the task is easy for you. And generating the examples and checking whether the task is done correctly, that's really easy for you. But you don't know how you do the task. So how can you express that to a computer? You can't solve it the old way. AI, the way we think of it today, is about succeeding at those complicated tasks that programmers cannot write instructions for by hand. And you need super flexible algorithms, neural networks, and that is part of a class of stuff called deep learning. It's part of machine learning. And so when people say AI today, they tend to mean deep learning. That's the way that it's used. So solving these really complicated tasks that you couldn't solve a different way, except by teaching the computer with examples. So this is about automating the ineffable. You can't say how that task should be done. You can't solve it the way that you do the calorie prediction. Now, I also want to point out something really powerful here. When we as humans communicate with one another, when we are trying to get another human to do something for us, we have two modes of communication available to us. Direct instructions, or, hey, look at a bunch of examples and you figure it out. And we use both as the situation demands. Before machine learning, we didn't have the ability to communicate that way with computers. All we could do is give the instructions directly. So that's like a huge part of our natural communication that we want to use, gagged. Think of this as an ungagging. Now, as a programmer, you can communicate with the computer two different ways. So don't think of this as something sci-fi and robotsy with a mind of its own. Think of it as unlocking a second way to get computers to do stuff for you. That's what we're about. And this is really powerful because it's a whole class of tasks that you can automate that you just couldn't automate before. So why now? I mean, these things have been around for a really long time. Neural networks were named in the 50s. Linear regression, Gauss was doing that 200 years ago. Why only now? Well, if you're going to build these more sophisticated recipes, you're going to need more. More sophisticated algorithms, more data, and more computing power than before. And until fairly recently, and I'm talking this decade recently, we just didn't have that. So I'd like to introduce you to 3 of my colleagues at Google who've been working in these 3 areas, and they, along with others, have been instrumental in changing all that so that science fiction is now here. So first off, Geoff Hinton. Geoff Hinton is one of the pioneers of artificial neural networks. Artificial neural networks, and that will be the last of the methods that we'll get a flavor sense for on our menu. They are essentially many layers of mathematical transformations. Not much to do with brains. But if you have all these layers of transformations, you effectively have a very flexible recipe. And if you have such a flexible recipe, you are able to fit those boundaries for a much wider, more interesting class of tasks. I mean, think of those surface boundaries with neural networks. You can pretty much sign your name in cursive, which you can't do with a bunch of lines. So you can solve more interesting tasks because these algorithms are very flexible. The price, though, is you do need more data and more computing power to make them tick. So introducing Fei-Fei Li. Now, Fei-Fei started her career as a computer vision researcher at Stanford. And, well, actually, when this was going on, Fei-Fei was at Caltech. And Fei-Fei was thinking about why a 3-year-old human child is just so much better at this cat-no-cat game than any computer vision system out there. And she realized that 3-year-olds have something that computers don't have. A loving parent who bothers to give them a bunch of nicely labeled examples to learn from. The parent is saying, no, sweetie, this one is a cat, not a dog. And she did a quick back-of-the-envelope calculation and realized that a human child would have on the order of millions or tens of millions of examples. She thought, okay, well, maybe that's why machines aren't succeeding. Of course, these computer vision folk who are trying to use a few thousand examples aren't going to get anywhere. You're not going to get performance like a 3-year-old. Based on that, fine. All I need to do is I just need to pick up a data set that's nicely labeled and big enough, and then off we go. All right, who's got this data set for me? It turns out people like their kids more than their computers and haven't bothered to make that data set. And so you can't have any progress. And Fei-Fei decided that she was going to change that. And whether or not they would force her out of grad school, she would sit there and organize a project around getting great examples, nicely labeled data that everyone could learn from. At some point in this project, she was running something like 60,000 mechanical Turk workers, all sitting there labeling things as cat, not cat, for you so you don't have to do it. And then when ImageNet, her project, launched in 2009, it had something like 2 million beautifully labeled photographs. And she made that available to everyone so that the whole community could make progress. But algorithms and data aren't enough. You actually need to be able to, lift and process that stuff. So you need the hardware and computing power. And Jeff Dean at Google is instrumental in the Tensorflow project. Now, Tensorflow, from the data scientist's perspective, looks kind of like most other data science frameworks, except much more finicky and annoying to program in. You force your data into the thing with some fuss, hit run, out comes a recipe, off we go. And you could probably do that in any programming language subject to your degree of masochism. That's not the part that makes TensorFlow magical. The part that makes TensorFlow magical is the way it uses the hardware. It doesn't waste it. What would have not been enough hardware, would have taken much, much longer, is now fast enough that this whole thing is viable. And then there's also this little bit about specialized hardware. And somewhere around 2010, some researchers noticed that the calculations that you need to do for neural networks are very conveniently performed on hardware that was developed for an entirely different industry, which is teenagers playing video games. And that's why you hear GPUs this, GPUs that all over this neural network space. Graphics processor units just happen to be pretty efficient for this, and so those researchers realized, Jeff Hinton was one of them, hey, if I just grab a standard gaming console and hack that thing, I've got myself a supercomputer for $300. And that's a big part of the birth of this AI revolution. So you've got the hardware, you've got the specialized processing frameworks, now open source, so everyone can use it and contribute to it. You've got the huge, beautifully labeled data sets and the algorithms. And with all that, the future is here, and now we can actually use this deep learning stuff for real business applications like cat, not cat. That's how the Google Photos thing works, where you can type in cat and it pulls up images of cats. But it's not all cat and no cat. Airbus, one of our customers, is in the business of making high-quality satellite image maps. And it's not a very high-quality map if it's covered in clouds. So you'd do a few flyovers, and you'd want to remove the cloud cover. But see, the clouds change, so does the snow, but you want the snow, and you don't want the clouds. And so then maybe, imagine this task, my friends, you have to do it. You go into the photograph and pixel by pixel determine which one is snow and which one is clouds. Is that a job you want? I mean, maybe, I don't judge you. I prefer to spend my time a different way. I would much prefer to have a machine learning system identify for me, hey, these ones are possible clouds, approve or deny these changes. So now I'm more the supervisor of the system rather than the manual laborer who has to do it all by hand. In communication, I don't speak Chinese, but I'm assured that this is not a word-for-word translation. You can use deep learning to capture meaning, power things like Google Translate, or cutting out communication drudgery. I know how you love to actually type out those words that you use over and over again in your emails. You prefer to write the full thank you rather than th. Now, to cut out some of those that drudgery, Smart Reply gives you those three options, and if one of them seems like what you were going for, you can select it, and if not, you just keep writing. So it helps you make your life less tedious. Playing games. This game-playing AI seems pretty frivolous, and yet the math powering this is pretty close to the math powering those self-driving cars. But you know, at Google, we let nothing go to waste. So we figured, how can we use this game-playing AI to do something useful? Let's give it a useful game to play. And the game we gave it was the game of data center. As inputs, it gets information about what's going on with the data center. Its joystick is the cooling system controls. And instead of that high score, its score is energy efficiency. Get the energy efficiency to be as good as possible. Now, before, the way to solve the problem of how can we make our data centers more efficient, it was a standard analytics approach where a bunch of analysts and a data science team would go and collect data and think about it and profile it really carefully, and then think some more, suggest some changes, test what that would mean, and they'd get maybe like a 1 or 2% improvement, which you shouldn't sniff at. A 1 or 2% improvement in energy efficiency in a data center is a huge thing. Huge cost savings and pretty good for the environment too. Now, when we gave this to AI, what do you think the improvement was? If you don't know the answer already, what would your guess be? I hear 15%. Bold, 15%. That's a lot of money saved. 15% going once. 15% going twice. Sold for 15%, except the answer is 40. Yeah, huge savings and an incredible reduction in carbon footprint. And there's so much more you can do with it. Have a look at all these different bits of inspiration, but I've got a different way to get you inspired as to how to get started. How do you find a machine learning use case? Here's what I proposed. Imagine that there is no machine learning. It's all a hoax. There's no AI, there's just a bunch of people on an island somewhere, sitting in cubicles behind computer screens, and you send them some information, like a photo of a cat, and they are going to con you and write back cat, and we're all going to pretend that that's the AI. Imagine that. The only way you can communicate with these people is to send them tasks by example. No instructions. You're not allowed to write instructions to them, but you can send them examples. If I allowed you to use this resource for almost free, and there were a lot of them, and they were very fast, you could really scale them up, what would you use these humans for? What drudgery would you cut out of your life? And as you're thinking about that, you're coming upon the right kind of applications for machine learning. But wait, you don't know how drunk these people are. So you can't just trust them with your important tasks. You need to check that they can actually do those tasks. And for that to work out, you need to be able to say what it means to do your task correctly. And if they make mistakes, which mistakes are worse than which other mistakes? And how would you like to score that performance? Because you're going to want to check whether this island can actually do the job for you. And if it can't, you don't want to hand over control of some important process to this thing. Now, you do see these creative applications like, hey, Drunk Island, write me a poem. And for those, you don't really know what it means to write a poem well. You kind of hope for something good to come out of there, but you're not sure what you're expecting. Well, for those things, you shouldn't really hand over the task entirely to this system. Instead, what you should expect is that it is just a way to inspire your human creativity. It's just going to mush up some information for you and propose something that looks like a poem. That's just some way of combining a whole lot of data. And you're going to look at this and you're going to actually use your own judgment as the human creative, and you're going to ask, does this inspire me? Can we work with this? And if it doesn't, you're going to kick that island, tell it, hey, go do this a different way. Over and over again, until something looks like it's worth pursuing. And then you're going to do that trick that all these other folks do, which is you're going to put that out there on the internet and pretend like that was the only version ever. Look at the poem machine learning wrote for me. Machine learning writes poems, says the newspaper heading. It's actually you that's writing the poem. Machine learning is just jumbling stuff up for you in some haphazard way, like monkeys on typewriters, just a little better because it's finding patterns rather than doing it purely at random. But it's a way to filter human creativity. That's how you should think of those applications, where we're not quite sure what we're looking for. There we have it heavily interfacing with the human, and the human is at both ends of the process. And what about this other kind of application where you have, hey, Drunk Island, generate for me the face of a celebrity who doesn't exist. That application's a real application. That works. The technique there is called Generative Adversarial Neural Networks, or GANs, and it's all the rage these days. Here's how to think about those. There are two Drunk Islands, not one. Drunk Island number one is taught to figure out whether the celebrity is a real celebrity or it's some fake generated image. So it's a thing labeler that's doing a bit of truth detecting, which one is legit, which one isn't. And the second Drunk Island is supposed to trick the first one, generate images that get past the other one's defenses. And both of them learn together and both get better at their game as they battle it out in cyberspace. And by the time they're done, the tricker is good enough at it to trick you. And its output looks kind of legitimate. Still the same kind of components. And still for both of them you need to be able to say, what does it mean for the first one to succeed? What does it mean to correctly identify the face? What is the other one trying to do? If you cannot say that, you will not be able to use machine learning to solve your task. All right, why should you trust machine learning? We have a particular problem. As we move towards the AI applications, we're beginning to automate the ineffable. That means that we are solving things where we could not come up with the recipe. I don't know about you. I take a pretty positive view of my species. And I imagine that we are actually fairly smart creatures. And if the recipe were simple, and there was enough reward in it, I imagine just through sheer bloody-minded stubbornness, we would find a way to figure out and handcraft that solution. So if we are forced to rely on something like deep learning to solve it, and we can solve it no other way, I imagine maybe that's because the underlying recipe is now so complicated that it's too much for us to read and think about. There's a memory capacity limitation in here. And so if that thing is really complicated, you can't really expect to open it up and read the recipe and go, aha, well, that's how it's figuring out what's a cat and what's not a cat. If the pixel in the top right-hand corner is blue, then it's a cat. It's not going to be that simple. You're not going to be able to read it and understand it. So you're not going to be able to base your trust of it on the recipe. You're stuck. Now, what I propose is that that's not a great basis for trust in the first place anyway. Think about going on a new kind of airplane. An entirely new kind of airplane. A spacecraft, let's do that. New kind of spacecraft. And you've got two options for the spacecraft you're going to sit in. Spacecraft number 1, all the physics is written out exactly for how it works. All of it is available and you can read that thick stack of documents. Spacecraft number 2, no information on how it works, but lots and lots of information about all the previous flights that it's completed successfully, all the trials, all the testing conditions. Which of the two would you like to trust yourself to? The one you know exactly how it works, but it's never been tested, or the one that you don't understand how it works, but it's been tested thoroughly? Number 2, I have a strong preference for number 2. For a lot of our medication, we have no idea how they work, we just know that it does work. That's good enough for us, as long as we can be sure it works. I submit to you that that is a much better basis for trust. Checking that it does work. Knowing how it works, that's a pleasant extra thing. But checking that it does work, that's what you should be basing your trust on. And so the analogy for thinking through this stuff in machine learning is the professor analogy. You already know all this stuff because you've taken exams, and if you've ever set exams, even better. So let's have a quick look. You're the professor, and your student is going to take a calculus exam tomorrow morning. So the student has written, luckily, something down from the board to study from. There we go, an equation. I said no equations, and look at me lying. So the entire job of the student, the machine learning system, is to go from the inputs, the left-hand side, to the outputs, the right-hand side, correctly. And so this is what the student's going to learn from, going to learn really, really hard, and find a pattern that works. You can just turn the 8 on its side, and there you go. And I want to point out that in these data, where the student is learning, training, it works. This is correct. 100% accuracy. Now, at this point, would you go to the exam if you were the student? I mean, I've certainly taught some undergraduates who I think would have gone to the exam. I've had to grade their papers and cry a little. But you, my dear enlightened audience, you wouldn't just go to the exam based on this, right? What would you do? What do I hear? Try another one, exactly. But there's an important difference between you and my student. My student also tries another one. They try it on the exam, where it matters. Whereas you have the wisdom to try it in the safety and comfort of your dorm room, check your understanding while you can still go back and adjust your model if you don't get it. So what you are doing and they're not doing is validation. That is what validation in machine learning is all about. A safe environment to try it out, where you're still allowed to go back because the stakes are not high here. A soft interim test. So let's try another one. apply our model. We get performance, and turns out that's not how math works. And based on this signal, we then can ask ourselves, fine, should we go to the exam or should we go back to training? Then the student sits there and tries out all these extra practice problems that you, the professor, have given to them. And finally, at 3 o'clock in the morning, you, the professor, get an email from the student. Validation passes. I did all of the practice problems correctly and all of the in-class examples correctly. Please give me my A+. I don't need to go to the exam because I've done it. And your response is? Of course not. Now why? Why do you say that? You say that because your student could have contorted their understanding to the in-class examples and the validation examples and just memorized the whole lot. Maybe even without realizing that they'd memorized them. Just formed some recipe, some model that fits what they've studied. It doesn't generalize to anything else because it's just some crazy mishmash of the peculiarities of those examples that they worked with. And you don't know if that's what they did because you know they were allowed to retry both the in-class problems and the practice problems many times as they want. You don't know what kind of mad logic is going to come out of that. Memorization is possible there. And so you, as a wise professor, are going to say, absolutely not. I'm so glad for you, student, that you feel like you've gotten yourself to a state where you're confident, that things look good for you. But to really make sure that I don't release any really bad students out onto the world, you should come to the exam and we'll check that you know it. Now, professors, you already know the requirements for the final exam questions. What has to be true about them? The most important thing. The student is not allowed to have seen them before. Because if the student has seen them before and knows the answer to them, the student could be memorizing. And your entire goal as a professor in this machine learning space is to make it so that your system cannot win by memorization. It cannot just do the look up the old answers insofar as I remember them and submit that as my new answer. And the only way you catch memorization is if you give truly new stuff for the testing. And that's why we have that separate test phase. Now, a lot of the pitfalls in machine learning tend to boil down to this learning and teaching thing. People just lose the common sense of learning and teaching. They don't think about that. They get so stuck in the math. So I implore you to think about this carefully first, and then you can think about the mathy stuff if you wish to. This is obvious when you have it spelled out for you, and yet you keep seeing these disastrous things over and over again that just are this. Obvious stuff. So let's look at these obvious things. First, you want a calculus-enabled student. You should use relevant examples. So the only thing that the student's going to learn is what's in the textbook you give them to study from. Just because you have textbooks doesn't mean your student is going to learn awesome stuff. What if those textbooks are Japanese-English vocabulary pairs? How is that going to help for calculus? Now, your student will be able to go and find patterns in that and learn it, but they won't do the task you need them to do. So we need to stop saying data with a capital D, like just having data makes things magical somehow. And even worse, data with a capital D plus the holy water of machine learning means it just works. No, data is just examples, information, and you are trying to express yourself by example. Your examples should be relevant. And so I say to Google engineers, if they're going near machine learning, they should consider tattooing this sentence on themselves. The world represented by your training data is the only world you can expect to succeed in. So you are in charge of what's in your training data. And if you pick a silly training data set, you're going to be able to succeed in the world represented by that data set. That's just not the reality that you inhabit. So your system's going to crash and burn in the real world. A classic example is one where you're interested in all your users, and the data that you choose to learn from is your users who inhabit an island near Antarctica or something, and nobody else. Those users might be something unique and special about them. They don't represent the whole world of what you're interested in, and you'll build a system that succeeds there, and then you'll be so surprised why it fails in New York City. That is your fault. You are supposed to open the textbooks, check that you like what's inside them. And a lot of this stuff about bias and fairness in machine learning also boils down to this. If you choose textbooks that are written, collected, curated in a way that reflects the biases of the humans who did that curation, your system's going to learn that stuff. And whose fault is that? Jointly, the author of the textbook and the professor who failed to check whether that textbook was something that you wanted to give to your student to study from. And so really checking your data, making sure that it's relevant, making sure that it describes the reality you want to succeed in, that keeps you safe. And it keeps you away from these surprises that people don't see coming that they really should have seen coming. The other one is catching memorization. The whole job here is not to parrot, but to succeed on new stuff. Otherwise, we wouldn't need machine learning. And you fail at your one job if your system can beat your test by memorization. So please design that test so it can't be beaten by memorization by having a truly pristine dataset to test on. If the system has seen the dataset in any context already, it is not okay for testing. And the system is jointly the algorithm and the human working on it. Because the human knows some stuff about how this context works and kind of knows how to arrange all the pieces so that they can get a good performance. If the human already knows too much about that data set, they know how to beat it. A good data scientist is a scary thing. Okay, what is decision intelligence? You might have heard of decision intelligence. And before we go there, you told me you took stats courses. Let's do a quick review of stats. Remember the errors in statistics. Type 1 error. What is type 1 error? Incorrectly rejecting a null hypothesis. What is type 2 error? Incorrectly not rejecting a null hypothesis. What is type 3 error? Statisticians? Correctly rejecting the wrong null hypothesis. Let me say that a different way. Using all the right math to answer the wrong question. Type 3 error is the one that really plagues data science today. We've spent so much effort developing the math, developing the algorithms, getting the data sets, figuring out the code. And we've spent almost no effort figuring out how to ask the right questions and how to run an end-to-end applied process without messing up. And so what you end up seeing is you have these folks who graduate from their PhD programs and they know how to very studiously, very meticulously do the math correctly. And they cheerfully go down rabbit holes doing that math uselessly because they're answering the wrong question with it. Decision intelligence is about fixing that type 3 error. It is applied data science augmented by the other sanity-giving sciences, like the social sciences and managerial sciences, to look at decision-making as a whole. So why do businesses fail at machine learning? It seems straightforward. These algorithms have been around for a long time. Well, it kind of boils back down to this stuff. What they don't tell you about machine learning is that there are actually two machine learnings. The research machine learning and the applied side, the decision intelligence side. And these are as different from one another as building microwave ovens and innovating in recipes in the kitchen at scale. And for the research side, you're building general purpose algorithms, microwaves, for other people to use to solve their problems. And you're trying to build that better and better microwave, and you have these benchmark data sets that your microwave has to succeed on. And of course, if you want to improve on today's microwave, you've got to know how it works. Because how are you going to improve on it if you have no idea how it works? It's impossible. And so to train you, it's going to take many years, and it's going to take graduate degrees as well, probably, if you really want to make cutting-edge stuff. And of course you need the details of that wiring diagram. And that is how almost every course out there teaches it. It is teaching you how to make the microwave. Fair enough. When there's not many microwaves around, if you want to use a microwave, you have to build it yourself first. But it's almost like no one thought about the era where finally we would have warehouses upon warehouses of these things, all waiting, ready to go. And still, all we're teaching the world is how to build more microwaves. Who's using these microwaves? And how do we start using them better? I mean, if you're going to run an industrial kitchen at scale, it's not trivial. There's a lot to it. And if your entire plan for doing that is that the first people you're going to hire is a team of 20 PhD researchers who've been building microwave components their whole life, and they're supposed to figure out how to make gorgeous dishes to satisfy your customers, I mean, what could possibly go wrong? Right? And that seems to be the approach that businesses are taking these days. It's this over-focus on building and understanding the algorithms, and going beyond that and going to the applied side is it's a matter of hope. The entire strategy here is hope. You hope that someone will spend their whole lives learning every little detail about how to make a better microwave, and at some point will transcend and become a great chef. And okay, some do, and sometimes you hire such a person, and you have an amazing chef and a well-running kitchen. Please don't pat yourself on the back for good decision-making. You did not plan that. It was an accident that your amazing microwave engineer happened to be a great chef also. So we need to start thinking about training people to look at the applied side. Don't over-focus on the algorithms. It's a good reason why in this course I took all the nitty-gritty of what's going on inside the black box and I moved it to the very end, and I'm going to exhaust you all first so you don't stay for it. Because it's not that important to the application. If you want to be a researcher, then you need to know it. If you want to use these things, then you need to focus more on process. And you need to focus more on teamwork and decision-making, and that is what this course is more about. Machine learning, again, is about explaining yourself with examples instead of instructions. And the way you stay safe when you automate the ineffable is that you test carefully and make sure that it does work. So the statistician has your back. At the very end of the day, we're going to check that the student knows it. Okay? Who sets the exam, though? Who decides what it means to work? Who tells the system what to optimize for? Because the only levers that you have to communicate your wishes are your way of saying, this is what it means to do well, here's your score, and here are a bunch of examples you should learn from. The decision maker on the project is supposed to do that bit. Now, decision making, as it turns out, is not something that you will pop into this world being fully knowledgeable in. It's both an art and a science. It takes some talent, but there's a lot of skill to it as well. And it is the decision maker who is responsible for this stuff. Are our decision makers today skilled? I want to ask you a question about workers. Which one do you prefer? A reliable worker or an unreliable worker? Which one is better? Reliable. Yeah? Any dissenters? Because I would say it depends. It depends on the quality of the decision maker. If you have a great decision maker, you want the reliable worker. You want the reliable worker who scales up really quickly and does what they're told, does exactly what they're told, and follows the instructions of that good decision maker. Scales up the intelligence of that decision maker. Unfortunately, something that's good at scaling up intelligence, machine learning, is also really good at scaling up stupidity. And if the decision maker doesn't know how to do their part, instead of good outcomes, you get terrible outcomes. And that all gets scaled up before anyone knows what hit them. And so there, with a bad decision maker, you want the unreliable worker. You want the worker that's not all in on the incentive function given to it by the decision maker, that instead wants to play with its kids and hang out on the beach and what was on TV yesterday and am I hungry, in addition to whatever they were told to do at work. Because all those unreliabilities, all pointing in different ways, people, you, unreliable workers relative to machine learning, all of you kind of cancel out the badness of the decision maker a little bit. It's hard to scale that stupidity. There have been cases in humanity's history where that got out of hand a little bit, but for the most part, you're the reason it's self-limiting. Machine learning, though, does what it is told, optimizes for what it is told to optimize for. And if the decision maker doesn't know how to ask, you have a problem. And that is why data science, machine learning, and AI future needs skilled decision makers. And needs good process here and teams who know how to actually carry this off safely and reliably. Decision intelligence is about wishing responsibly. And I think of machine learning as a bit of a proliferation of magic lamps. It's never the genie that's dangerous. A genie can be told to do fabulous, lovely things for the benefit of all of humanity. What's dangerous is the unskilled wisher. And not necessarily even the wisher who has some malicious intention. The wisher who doesn't think through what they're asking for, who thinks it sounded good in their head and I'll ask it and that'll be fine. So here's a classic example. We use this in our machine learning training all the time. It's the parking lot example. Your business has a parking lot, 1,000 spaces in that parking lot. And it's in a pretty busy place, so at any given point in time, about 10 of them are empty, on average. And what you want to do is you want to have a big sign out there on the outside of your business saying how many empty parking spots do you have right now. And you're going to use machine learning and have a camera on the top and it's going to do some thing labeling for each spot. Is there a car in the spot right now, yes or no? So that we can put an accurate count. How many spots are available here right now? And then you're like, okay, what metric should I use? Accuracy sounds good. Yeah, accuracy is nice sounding. And how accurate should I ask it to be? They use 95% in all my stats courses. That seems like a good number. I'm going to require at least 95% accuracy and then I'll launch this thing. Who sees it? Anybody? I'm looking for the horrified expressions. Who sees why the business is about to go under? A skilled decision maker with the skills we're talking about here should see it immediately. How do you beat that requirement if you are trying to simply game that scoring system? If you have no honor and no virtue, like the board game power gamer that you never want to invite over, right, who wins every board game playing with their unfun strategies. If you want to look at it from that perspective, what's the way to win? The cheapest, ugliest way to win against that scoring system? You need to get at least 95% accuracy. Just say they're all full. Because what's that accuracy going to be on average? 99%. On average, 10 are empty at any given point in time. So just by saying all 1,000 are full, you only get 10 mistakes out of 1,000. That means 99% accuracy. That beats the 95% requirement. It passes the exam. Here's the exam, it passes it. And off it goes, cheerfully, labeling 0, 0, 0, 0, 0, and your parking lot dies. Now, whose fault was that? It was the wisher's fault. Whoever thought that it was a good idea to use those examples and that incentive structure. And that's what we have to spend a lot of time thinking about. For an AI future, there's a lot of microwaves already. And we're so focused on building those well. And then we're a bit focused on the testing and the statsy stuff on the other side. We should be more focused on that even. But this first bit, what should we build? How should we check? How do we diagnose what we're wishing for? That we don't spend enough time on. And that's probably the most important bit. And that's how all your projects don't end up imploding. Now, to carry this off, you need to appreciate how crucial skills diversity is. This is a team sport. In fact, my least favorite question in machine learning is the one where you go, Cassie, describe to me what the ideal machine learning hire looks like. And I hate that question because it suggests that this is a one-person game. It really isn't. It's also not a game where you want multiple copies of the same person. Stereotypical computer science, machine learning professor type, you just get 20 of them and everything will be great. There is a real diversity of skills that is required to carry this off successfully. And if you don't cover them on your project, you're going to have a problem. And you might have them all represented. If you haven't thought through how to make them work effectively with one another, you're also going to have a huge problem. Things are just going to fall down the gaps in between these people. You need those perspectives, you need those decision skills, you need the data science, you need the social sciences, the managerial sciences, the reliability folk, the engineers, you need all of it working together. So what does our future look like with machine learning? We are moving towards more application. We're moving out of the pure research era to the applied era. I hope that this also comes with literacy all around. Machine learning isn't for the select few, that everyone has a basic understanding of the core principles, and not how the nuts and bolts work inside the thing, but what it actually means. That it is explaining yourself with examples. We love democratization. That's a good thing. Everyone should be part of this. We're making it easier and easier for people to have that second mode of communication with machines. That's great. The tools are going to get easier, and they should. And I'm a big fan of our push to make them easier. There's no honor in doing something the hard way when there is an easy way. And those of us who can apply our engineering effort towards making the easy way easier, our hard work is well spent that way. I expect that there will be a lot more emphasis on giving everybody tools. But now that everybody has tools, now you can scale up either the intelligence or the stupidity of their application. How do we think through doing that well? Well, we should think of it in terms of process and interdisciplinary stuff. That's what this course is going to be about. It's going to be a 12-step course. All my courses are 12-step programs for taking an idea from conception to having it running successfully in production. And we're going to use a kitchen analogy to also set our expectations for how this process is going to look. So we'll dive into the process after the break, which is coming in 3 minutes, but we'll set our expectations here with this analogy. Say you want to create a recipe for sausage. And there may be vegans in the audience, so we will make it vegan sausage. And the sausage is not only vegan, it must be low-calorie, gluten-free, sugar-free, and Michelin star compatible. The goal. Our goal is to innovate in the kitchen with recipes. We can afford all kinds of microwaves and whatnot, and we have that in our lovely kitchen. What is the process actually going to look like? Do you know how long it will take to get you that sausage? Can you look up the solution in a textbook and really think through the biochemistry one time and just do it once? Are you even sure that your endeavor will succeed? But how will you go about it? Well, the same way as how you go about machine learning. So let's say a preview of these 12 steps. And of course, I love 12-step programs here way too much. I force all my courses into them, and this should really have been 13 steps, so we started step 0 to make it work. So our steps, a preview of what we're going to dive into in detail after the break. Step 0 to 1. Asking the right questions in the first place. Like, what are we trying to make? Which customers are we trying to please? What does it mean to succeed at this sausage? Do we have standards? That kind of stuff. 2 through 4, getting the right ingredients. And when we talk about getting the right ingredients at scale, there may be a lot to it. We're not going to, because this course is not a data engineering course, I'm not going to cover that in tremendous detail. I want to give a nod here to how hard this actually is at scale in practice. Data engineering is not a trivial thing. I mean, at small scale, it's, can I download the spreadsheet and open it on my laptop? Yeah, sure. It's just when the scale gets big, it becomes quite a sophisticated discipline in its own right. So we're getting the ingredients, we're sourcing them, and ingredients matter, right, chefs? They matter a lot. Just because I have ingredients, I'm going to be able to have my vegan sausage. True? No, certainly not true. Steps 5 through 7. Tinkering in the kitchen, trying different stuff, and iterating towards a better recipe. 8 through 9. Actually, maybe taste it first before you subject your customers to it. So, a soft taste test, validation, the chefs in the kitchen are doing it themselves. The testing is a much more rigorous, strict process of should we actually even be putting this in front of customers. 10, streamline your kitchen so you can start serving this. Your productionization step. Because your thing that you made in a bowl is just a prototype. And if you're actually going to do this seriously and at scale, you need to think about rearranging the kitchen. And that is going to be quite an investment, which is why tasting it carefully beforehand was kind of important. You need to know whether it's worth arranging your whole kitchen and menu and everything else to be able to serve this dish. Then, actually try it on some customers first, as produced by this streamlined process of yours, to make sure that the customers like it enough for you to make it a permanent fixture on your menu. Don't just add it to your menu and hope. There might have been some bugs introduced into how you arranged your kitchen. Or maybe your customers just hated the dish, and you didn't realize that because your prototyping process didn't reveal it to you. And then finally, it's going to be the gift that keeps giving. You're going to have to maintain and monitor this thing in perpetuity, and your world is allowed to change. You were expecting that you can source rice, and suddenly there's no more rice in the world. Well, what are you going to do about it? What's your plan? I hope is not a strategy, you need a plan. And how do you think through that planning? And that's what we're going to cover after the break, and I'm here for questions.